Chapter 11, Oscillation and Waves. What we'll do this chapter is we'll introduce a type of motion that's going to be called simple harmonic motion. You also see SHM for the abbreviation of it. We'll be looking at motion that is oscillatory. We'll talk about energy in oscillatory motion, a couple of examples of oscillatory motion. One of them is a pendulum, so we'll talk about that. We'll talk about harmonic motion that can be either damped or forced. It's called resonance. And then we'll move on and introduce the second major topic, which is going to be waves, the types of waves, how energy is transmitted by waves, and how waves behave when they interfere with each other, setting up standing waves, diffraction and refraction of waves, and lastly, how we can describe a traveling wave. So simple harmonic motion, or SHM as it's very often abbreviated, is simply going to be motion that is repetitive. An object that travels back and forth over the same path, taking the same amount of time, is going to be called simple harmonic motion, also called periodic motion. And the mass on a spring is going to be a great example. You can kind of see that this mass is going to go back and forth and back and forth and back and forth. So what do we need physically for simple harmonic motion to occur? We're going to need an equilibrium point for the mass on the spring. That's simply going to be the unstretched length of the spring. And we're also going to need something called a restoring force. And this restoring force is going to always want to return the object to its equilibrium point, which in this setup right here is going to be this point, the point of the unstretched spring. And you kind of know that if you pull a spring back to this point right over here, then it's going to have a spring force. That spring force is going to be towards the equilibrium point. You let go of it, and the spring is going to compress. Now the spring force is pushing the spring back to the equilibrium position. So we have everything that we need by having an equilibrium point and by having a restoring force that's going to always point towards the equilibrium point. Of course, we are assuming that the surface is frictionless, and the equilibrium point again is simply going to be that x is equal to 0. We can write Hooke's law and see that if x is going to be positive, that the force is going to be in the negative direction, and if x is going to be negative, then the force is going to be in the positive direction, and lastly, if x is equal to 0, the force is also going to be 0. So it's at the equilibrium point, it's not going to experience any force, and if it's moving in the positive direction, the force is going to be in the negative direction towards the equilibrium point, and vice versa. Let's just get some pesky definitions out of the way. Here we have our mass on the spring showing us this simple harmonic motion, and you can see that the force is always towards the equilibrium point, and the mass on the spring is essentially going back and forth here. We're always going to define our displacement as being measured as away from the equilibrium point, which is going to be the unstretched length of the spring. I've kind of drawn a line through it right here. So here the object is in its equilibrium point, and here we'll define the amplitude to be the maximum displacement away from the equilibrium point. It's going to be these 2 points right there. See that x is equal to capital A. So amplitude would typically be in meters. And we've said that it's going to be periodic, and it's going to take the same amount of time to complete one full cycle. When I say one full cycle, I mean it's going to start out at some position. It's going to be negative A. It's going to go through the equilibrium point. It's going to go through. It's going to reach the stretched side of the spring. Now it's at positive A. This is defined to be 1/2 of the cycle. It's going to go back, and at some point it's going to be at the negative amplitude again. That is the definition of one full cycle. I've said that it takes the same amount of time to complete each cycle. This is going to be called the period. The symbol is going to be capital T, and period is going to be measured in seconds. It's really kind of seconds per cycle, if you will. Another way to describe this is going to be with an object's frequency, a symbol of an F, and that's going to be the number of cycles per second. So 1 per second. The cycle is often not written. This has another definition. It's going to be how many hertz an object is, where hertz is 1 per second. And you'll see that very typically that a spring will oscillate back and forth with, say, 20 hertz. We can relate the period and the frequency fairly simply. The period is going to be 1 divided by the frequency. We can still hang the spring vertically, or we can hang the mass vertically. All that we're really doing is we're changing the equilibrium point. The unstretched spring would initially be here. Now we hang a mass off of it, and the mass obviously has some weight, so it's going to stretch the spring down, and now the spring is exerting a force upwards, but now it's balancing gravity. If I take my spring and I give it a pull down, the spring is going to pull it back towards now this equilibrium point, and if the spring compresses, the force is going to be downwards, again going now towards a brand new equilibrium point. It's still going to be what we call simple harmonic motion. It turns out that any system where the restoring force is proportional to the negative of the displacement is going to be called simple harmonic motion. I've already talked about that. The object that is exhibiting this behavior is going to be called a simple harmonic oscillator. We've already talked about one. It's going to be a mass on a spring. Another one would be something like a pendulum. We'll talk about that one in a couple of slides, but if you think about that, the pendulum is going to have an equilibrium position. That's going to be right here. And then if you pull it off to the side, the restoring force is going to point towards that equilibrium point. Same with over here. Let's talk about energy in simple harmonic motions. We know that we can write the potential energy of a spring simply as 1/2 kx squared. We also know that if the object is moving, it's going to have a kinetic energy of 1/2 mass velocity squared, and energy is going to be totally conserved in the system, so we can write the total mechanical energy to simply be the sum of these two types of energy, and this is going to be the total energy in the system. It can slosh back and forth between potential energy and kinetic energy, but the sum of these will always be a constant value. At the two extremes, all of the energy is going to be stored in the spring energy, and at the middle, where the spring is not going to be compressed at all of the energy is going to be kinetic energy. And the same with at the other equilibrium point, when the spring is stretched out all the way, all the energy is in the spring energy. It's not moving. Its velocity is actually going from positive to negative, so the velocity is 0. And at some middle point, the energy is going to be the sum of those two, but the energy will always be a constant value. If we know how far away if we know how what the amplitude of the sky is, we can very easily find the energy of the system. It's simply going to be 1/2 kA squared. Again, the velocity is going to be 0 at the turnaround points. We can use this idea, knowing what the amplitude is, to figure out what the total energy of the system is. What we can then do is we can say, you know what, I know that the total energy is going to be conserved, so I can write the kinetic energy of the spring plus the potential energy of the spring must be equal to that total energy. At the point where the string is not stretched at all all of the energy is going to be kinetic energy, so we could write what the maximum velocity would be. In this case, the maximum velocity is simply going to be equal to the square root of k divided by m, and the a was squared, so that comes out of the square root, and we can write what the maximum velocity would be in terms of the spring constant as well as the mass. And actually, in general, we can figure out what the velocity of the mass will be simply knowing the position of the spring, essentially solving this equation right here without having x equal to 0. We can consider another example that's going to have behavior that looks like simple harmonic motion of an object that's being swung around on a table. It's got some maximum velocity that's never going to change, but the direction of the velocity vector will. It's going to go around the table, essentially taking the same amount of time to complete each revolution. It's always going to come back to some point, and it's just going to have this repetitive behavior. If you're an observer kind of staring end on at it, you would say that its equilibrium position is going to be right here, and you're going to see it essentially oscillate back and forth, having some maximum velocity at the middle and essentially having no velocity at the end. So we can write the velocity in the exact same fashion as simple harmonic motion. The book goes ahead and shows you how we can use this to figure out how the period and frequency are related to the spring constant and the mass. I'll let you read it on your own. In short, it turns out we can write the period as being related to 2 pi and then the square root of the mass divided by the spring constant. Intuitively, it makes sense. If you increase the amount of inertia that an object has, if you increase the mass, it's going to take it longer to make a complete cycle on a spring. Or if you increase the spring constant, you make the spring essentially more stretchy, then that would also increase the period. So it really kind of makes sense. So a very important equation to know and be able to use. Frequency is simply going to be 1 divided by the period, so we can write the frequency as such. One thing to remember is occasionally it's useful to write things in terms of their angular frequency, which is going to be 2 pi multiplied by the frequency. So this animal right here, this square root of k over m, is also going to be the angular frequency right there. We can also use the circle analogy to come up with a description of the position, the x, as a function of time, and you can see that it's related through a cosine. The position is going to be equal to the amplitude multiplied by the cosine of the angular frequency multiplied by time, remembering that the angular frequency is related to the spring constant divided by the mass and the square root, of course. We know that the angular frequency is related to the frequency, which is also going to have a reciprocal of period. So any of these three equations is going to be valid to describe simple harmonic motion, and you can see that it's related to a cosine, so there's going to be some sinusoidal nature to simple harmonic motion. If I gave you a functional form and said that the position is going to behave as such, cosine of 8t, I could say, okay, what is the amplitude and what is the frequency of this mass on a spring? We can simply look at, let's go for this guy, we can simply look and say that the amplitude is going to be 0.3 meters, and 2 pi multiplied by the frequency must be equal to 8, so the frequency is going to be 1.27 hertz, and the period will then be 0.785 seconds. we know that the period and the frequency are related to the spring constant and the mass, so then if we knew either the spring constant or the mass, we could figure out from these what the spring constant and mass would be. If we took a look at the mass on the string that's essentially going up and down, and we traced its position on some paper, the paper kind of moved in that direction, you would see indeed that the position is going to behave as a cosine, essentially as the mass on the string goes up and down. The period is going to be how long it takes it to undergo one cycle, so you can see the period right there. At half the period it's going to be at the other end point, and 1/4 and 3/4 of the period it's going to have the maximum velocity. This doesn't necessarily have to be a cosine. If we started taking data if we started the paper traveling when the object was at the equilibrium position, it's going to look more like a sine. So another way we could write this would be amplitude multiplied by the sine of omega t. So this is also a valid descriptor of simple harmonic motion, either a sine or a cosine, and again that's going to be the angular frequency multiplied by time. The velocity and acceleration are also related to the displacement. There's a little bit of calculus going on behind that, so I'm simply just going to throw these equations out there. We can say that the velocity at any given time is going to be the amplitude multiplied by the square root of k divided by m multiplied by the sine of omega t, or the acceleration, and the acceleration is going to be equal to negative k a divided by m multiplied then by the cosine of omega multiplied by t. This is for a position being equal to the amplitude multiplied by the cosine of omega t. And we can see that when an object is at its maximum amplitude, it's going to have zero velocity. When it is at 1/4 of the period and it's essentially at the equilibrium position, it's going to be moving the fastest, and so on and so forth. The maximum acceleration is going to occur when the string is stretched as far as it is, and it's going to be negative. It's going to be towards the equilibrium point. The acceleration will be 0 when the string is not stretched at all. Essentially, no stretch, no force, no acceleration, and so on and so forth. Another harmonic oscillator is going to be the simple pendulum. A couple of basic assumptions is that the cord is going to be massless and does not stretch. In that case, we can say that the pendulum is going to have an equilibrium position just straight down like a plumb line. And if we take that mass and bring it off to the side over there, we can break the forces up into components. We'll have the mass and gravity cosine theta be equal to the tensional force, and the force that is returning it to the equilibrium point is actually going to be mass times gravity times sine of theta. And here you're thinking to yourself, wait a minute, I need the force to be proportional to the displacement. Well, turns out that for small angles, sine theta and theta are essentially very similar enough that we can say that sine of theta is approximately equal to theta, and we can write our force to be equal to negative mass times gravity times theta, and you can see that this equation right here does indeed look like a harmonic oscillator should, a simple harmonic oscillator. This table right here is just kind of showing you, take a look at it, theta and sine of theta are very similar up until what, 15-20 degrees or so. So we can treat a simple pendulum as a simple harmonic oscillator. essentially what we're doing, essentially what we can do is we can say that the effective spring constant is going to be related to the mass, gravity, and the length of the pendulum. So we can come up with expressions for the period being related to the length of the pendulum as well as the gravity, two very important equations to be able to use. And essentially what that's saying is if you shorten the length of a pendulum, it's going to have a shorter period. Kind of makes sense. And if you take this pendulum to, say, Mars with a lower gravity, that's going to essentially lower the period of the pendulum as well. One thing that you saw in the last slides is mass doesn't matter. The period is not going to depend on the mass on the string as long as the chord is massless and the amplitude is small. The period is only going to depend on the length and the gravity, not on the mass. Of course, in the real world we do have friction, and so we can have damped harmonic motion, and if you go on to take higher level physics classes, you get to treat damped harmonic oscillators as well as driven harmonic oscillators, so good things to look forward to. Kind of conceptually, you can see that the position versus time is just going to get smaller and smaller and smaller and smaller, and you know this if you ever watched a pendulum in real life. Essentially, we're saying that the position is going to have an envelope that's going to now have an exponential exponential decrease with time. Sometimes we want damped harmonic motions. For example, your car. You hit a bump and you don't want your position versus time to do something like that. If you've ever ridden in a car like that, and I've owned cars like that, it's a little bit annoying. You want to instead have what we call critical damping, where you reach the equilibrium as fast as possible. If your car shocks are overdamped, then you hit a bump and essentially it's not going to give that much. That's called overdamping, and the system is just slowed so much it takes a long time to get to equilibrium. Lastly, we can have forced oscillations, which is also known as resonance. Essentially, vibrations are going to occur if there's a periodic driving force. This force may or may not have the same period as the natural frequency of the system. However, if you drive a system at its natural frequency, the amplitude can become quite large. And if you look at figure 1120, there's a bridge where the wind is applying this periodic driving force, and it is causing the bridge to become quite unstable. This is actually called resonance. Musical instruments, they depend on this phenomenon called resonance. Television stations also depend on it as well. Sometimes it's a good thing, sometimes it is unwanted.